Let's take a look at a couple more examples from this section. So, consider the function f of x equals to 8 times the quantity x minus 2 raised to the 2/3 power. Find the interval or intervals where f is increasing and decreasing. So by now, we should hopefully know that when we're looking at intervals of increasing and decreasing, we need to examine the first derivative. And more specifically, we need to start with the critical values. These are when the first derivative is equal to 0 or when the first derivative is undefined. Because this is where the function, these are your turning points, so where the function goes from being increasing to decreasing. So let's find the first derivative. You multiply 2/3 times 8, so 2/3 times 8 is like 8 over 1. 2 times 8 is 16. 3 times 1 is 3. So we get 16 over 3 times x minus 2. And then we take the 2/3 and we subtract 1, which is like 1 over 1. If you get a common denominator, you get 2/3 minus 3/3, which is a negative 1/3. So f prime of x is equal to 16 over 3 times x minus 2 to the negative 1/3. We don't want to leave that negative exponent, so we're going to move it to the denominator. And this will give us 16 divided by 3 times x minus 2 raised to the 1/3 power. That is our first derivative. Now, automatically, I can tell that the first derivative is going to be undefined. This happens anytime the denominator could equal to 0. So we want to think about, when does this equal to 0? Because then we will have division by 0. So x minus 2 will equal to 0 when x equals to 2. So in here, the first derivative is undefined. So that is a critical point. First derivative is also undefined when the 16 over 3 times x minus 2 to the 1/3 is equal to 0. So to solve that equation, first thing we do is we move this to the other side. We don't want it on the denominator, so we're going to multiply both sides by 3 times x minus 2 to the 1/3. But if I multiply this with the 0, 0 times anything is going to be 0. 16 can't ever be equal to 0, so there's no solution over here. So we only have one critical value, which is going to be x equals 2. So let's go ahead and plot that. So this makes two different intervals. The one interval is going to be negative infinity comma 2. The other interval is going to be 2 comma infinity. We need a test point in each interval, so let's just keep this simple. Let's pick x equals to 1, and let's pick x equals to 3. When you're looking for increasing and decreasing, you're interested in the first derivative. So f prime of 1, you would put the first derivative, which is this thing, into Desmos. Then you would put f prime of 1, and that comes out to be negative 5.33. This is a negative value. This tells us, remember, first derivative is a slope of the tangent line. So if the slope of the tangent line is going to be negative, that means the actual function is going to be decreasing. That's why we get the slope of a tangent line as being a negative. When x equals to 3, we want to find out what is f prime of 3, and this equals to 5.33, positive. So because this is positive, this means that the first derivative is slope of the tangent line. Slope of the tangent line is positive. The only way that can happen is if the function is increasing. So we're going to make a conclusion about f of x. In the first interval, this is decreasing. Second interval, this is increasing. Okay, so decreasing on the interval negative infinity comma 2, increasing on the interval 2 comma infinity. Next, find the interval or intervals where f is concave up and concave down. So anytime you want to determine concavity, concave up, concave down, this is the second derivative test. So let's take the second derivative. Our first derivative, f of x, or f prime of x rather, our first derivative is equal to this whole quantity which is 16 over 3 times x minus 2 raised to the negative 1/3 power. To find the second derivative, we are going to take the negative 1/3 and we're going to multiply it with the 16/3. So let me do the work on the side. If I have a negative 1/3 times 16 over 3, this gives me negative 16 over 9. So my second derivative is going to be negative 1/3 times 16 over 3. That's a negative 16 over 9 times x minus 2. Then we take this negative 1/3 and we subtract 1 from it. So 1 over 1, if you get a common denominator, this is like a 3 over 3. This gives us a negative 4/3. So the exponent here is going to be negative 4/3. And we don't want to leave a negative exponent, as we know. So our second derivative, we got the negative 16 on the numerator. Denominator, we have 9, and then this moves to the denominator, so it's going to become x minus 2 to the positive 4/3. This is our second derivative. Now the inflection points, this is where concavity changes from negative to positive, or concave up, concave down, or concave down to concave up. The inflection points occur when the second derivative is equal to 0, or when the second derivative is undefined. So let's first look at this case, f double prime of x equal to 0. So if we set the second derivative, which is negative 16 over 9 times x minus 2 to the 4/3, if we set that equal to 0, we'd have to multiply this to the right. Your denominator has to multiply to the right. We get negative 16 equals to 0, which can't happen, so there's no critical value, or there's no inflection point there. Now, f double prime x can be undefined. It's going to be undefined when the denominator is equal to 0. So we want the x minus 2 to equal to 0. That's what's going to make the denominator 0. So when x equals to 2, then the denominator will be 2 minus 2 is 0. 0 times anything is 0. So that's going to make the denominator equal to 0, which will make f double prime x undefined. So that's our only inflection point, x equals to 2. So let's take the inflection point, which is 2, and we are going to write the interval as before. So this interval is negative infinity, comma 2, and this interval is 2, comma infinity. Pick a test point. As before, pick x equals 1, x equals 3, but this time, when we're doing concavity, you don't want to do the first derivative, you want to find the second derivative. So f double prime of 1 and f double prime of 3. Once again, take the second derivative function, put it into Desmos, and then find f double prime 1, f double prime 3. So f double prime 1 is going to equal to negative 1.78, and f double prime of 3, this is going to equal also to negative 1.78. It's kind of weird. So this means that in both intervals, the function is going to be concave down, which means it's going to have an M shape. Now, just to make sure we did this correctly, let's verify this using Desmos. Okay, so let's go to Desmos and put in our function. So our function is this. It's f of x. So we're looking at the original function, not the first or second derivatives. Those are only to help us determine the increasing, decreasing, concave up, concave down. So the original function is f of x equals to 8 times x minus 2, and that's raised to the 2/3 power. All right, so let's go back to our work here. So we said that the function is decreasing on negative infinity, comma 2. It's increasing on 2, comma infinity. Let's see if that's correct. Function is decreasing from negative infinity to 2, increasing on 2 to infinity. All right, that looks great. Then we said that on both intervals, the function is concave down. So let's see if that's correct. If I zoom out a little bit, this is part of an M shape. Okay, so it's concave down. This is also part of an M shape. right? Like if M goes like this, so both ways, this is part of an M shape, so these are both going to be concave down. In other words, if I take any point here and I get the tangent line, it's going to be above. Here, it's going to be above. So these are both going to be concave down. So it looks like we did this problem correctly. Okay, got one last example, which I'll start. I don't know if I'll have time to finish it because I do get cut off at a certain point. So let's find the intervals where f is increasing and decreasing. So by now we know this is the first derivative. So let's take the first derivative of this, which is going to be 90 x to the 9th minus 9 times 2 is 18 x to the 8th. When this is equal to 0 or undefined, we get our critical value, which is our turning point. This can't be undefined because we're not dividing by a variable, but we can set this equal to 0. So when we do this, we have to first try to reduce this. So 90 and 18, we can divide these both by 18. So the 0 gets divided by 18 also. So this gives you 5x to the 9th minus x to the 8th, and that's equal to 0. Then we take out the greatest common factor, which is x to the 8th. So if you take out the greatest common factor of x to the 8th, we're left with 5x. X to the 8th divided by x to the 8th is 1. So remember there's a 1 left over, and we get that equal to 0. By the zero product property, either x to the 8th has to be 0, which means x is going to be 0, or 5x minus 1 has to be 0, which means x is going to be 1/5. So these two values, these are going to be our critical values. When we have our critical values, we are going to put them here. So we have 0, we have 1/5, which I'm going to convert to a decimal. That's going to be 0.2. And then we make our interval. So this interval is from negative infinity to 0. The middle one is from 0 to 1/5. And then the last one is from 1/5 to infinity. So these are the three intervals. Let's pick some test points. So here I picked x equals to -1. Between 0 and 0.2, like the only really one we can pick is 0.1. And then to the right of 0.2, I ended up picking x equals to 1. Increasing, decreasing, this is the first derivative test. So I calculated f prime of -1, and that equal to -108. Then I calculated f prime of 0.1. This gave me like -9 times 10 to the -8. Again, it doesn't really matter what the number is. All we care that it's negative. And then x equals 1. It just gave me 72. So this is going to be positive. So negative means the function f of x. Here it's going to be decreasing. Here it's going to be decreasing. And here it's going to be increasing. So it's going to be decreasing on the intervals negative infinity, comma 0, and also from 0 to 1/5. And it's going to be increasing on the interval 1/5, comma infinity. We can check that later on. Next, we want to find where is this concave up and concave down. So our first derivative, f prime of x, this is equal to 90x to the 9th minus 18x to the 8th. So if I take the second derivative, f double prime, this gives me 810x to the 8th minus 144 x to the 7th. This can't be undefined because we're not dividing by a variable, but you can set it equal to 0. Now I'm running out of time, so I'm going to skip a couple steps, but you would factor out the x to the 7th, and you're going to get x equals to 0, and you get x equals to 8 over 45, which is going to be 0.1778. So these become your inflection points. So we got 0 and we got 8/45. Rest in